Hey guys, welcome back to the Underswell. I'm Derek Sabori, and today I'm so excited to share a new video with you. This one, sort of an explanation video. It's a little breakdown of some scientific terminology that we hear about when we're talking about sustainability and when we're talking about climate change. Ocean acidification. What is ocean acidification? Well, today, let's dive in. I'm gonna give you a brief little breakdown and try to explain it the best I can so that you can explain it to others when talking about the impacts that come along with global warming and climate change. All right, you ready? Let's dive in. So, as you may know, when it comes to climate change and global warming and the release of greenhouse gas emissions or carbon dioxide into the atmosphere, our oceans absorb about a quarter, 30% maybe, of the carbon dioxide that us humans produce and put into the atmosphere by burning fossil fuels each year, right? At first glance, that seems like a really good thing, something that we can be really thankful of and we can really appreciate the ocean for. The problem is this significant uptake of CO2, this is changing the basic chemistry of our oceans. In fact, scientists estimate that carbon pollution, it's causing oceans to acidify faster than they have in 300 million years. And in the past 200 years alone, ocean water has become 30% more acidic, and that's faster than any known change in ocean chemistry in the last 50 million years. And that is essentially what this topic is about, ocean chemistry. So sure, the carbon cycle, this is a natural and important one. Carbon, after all, is one of the building blocks of life. The problem now is that CO2 is being created faster than it can be absorbed through natural processes, right? So it is the excess carbon dioxide in the atmosphere that is the problem. Now, ocean acidification, it's sometimes referred to as climate change's evil twin or famous cousin because they actually seem to go hand in hand, unfortunately. But what is it exactly? What is ocean acidification, and how do we break it down and explain it to others? Well, like I alluded to, it's a chemical process that changes the properties of seawater or ocean water. Ocean acidification refers to a reduction in the pH balance of the ocean, this over an extended period of time. Acidic solutions have a lower pH value, right? So while basic or alkaline solutions have a higher value. If you think of the pH scale, a 1 is the most acidic things can be. And the higher, which is 14 on the scale, the higher, that means the less acidic it is. So the lower the pH value, the more acidic the ocean is. Ocean acidification then is the lowering of seawater pH or the acidic value. So more hydrogen means a lower pH or higher acidity, and also carbonate saturation, which is needed for coral building. Each of these result from increasing atmospheric CO2 concentrations. And so, to be clear, seawater that has more hydrogen ions has a lower pH and thus is more acidic by definition. In fact, the definition of acidification terms, acidity, hydrogen, pH, are interlinked. Acidity describes how many hydrogen ions are in a solution, and an acid is a substance that releases hydrogen ions. And pH, well, this is the scale that is used to measure the concentration of hydrogen ions. And I know I'm not a chemistry teacher, and I know this is not a chemistry course, and that's not what you're here for, but try to follow along and keep this all in check. All of this is caused primarily by uptake of CO2, carbon dioxide, from the atmosphere. This is the sequestration that oceans perform for us. Again, something we're really thankful for. The oceans absorb that excess carbon dioxide that we're putting into the atmosphere. The ocean absorbs heat. And so when carbon dioxide mixes with water molecules, it forms something called carbonic acid. And if you can start to look at the chemical compounds, you'll see that that then breaks down easily into hydrogen ions and bicarbonate. So essentially, carbon dioxide plus water equals carbonic acid, right? And carbonic acid is weak compared to some of the well-known acids. Carbonic acid rapidly dissociates, or it splits apart, to produce bicarbonate ions. And so that carbonic acid, when it splits into bicarbonate and hydrogen, two different things, then those hydrogen ions, those bond with other molecules that are in the area. In turn, bicarbonate ions can also dissociate into carbonate ions. Now, carbonate ions are a key component of calcium carbonate. We need calcium carbonate to make shells for all of the shell makers in the oceans, corals, mollusks, anything that requires a shell around it or that has a shell base. Corals, as we know, are important to ecosystems, and all of those other elements, all of those other organisms that rely on shells, those create biodiversity to strengthen that ecosystem. When we have a strong ecosystem, we will have a strong ocean. And we know what we get from oceans: food, transportation, recreation, and just it's an essential part of life, and carbon sequestration. So both of these secondary reactions, which are the creation of carbonic acid and carbonic acid breaking down into bicarbonate and hydrogen, and then that bicarbonate breaking down into carbonate ions with hydrogen, both of those produce hydrogen ions and therefore lower the pH of the solution, like we talked about earlier. And the water is now more acidic than it was. Remember that pH balance that we talked about? And those available hydrogen ions, those are attracted to and they bond with other carbonate ions to form more bicarbonate. The problem with that, carbonate ions are needed to form calcium carbonate for corals and shell makers. The mineral calcium carbonate, this is a fundamental building block for numerous marine organisms, from microscopic algae to reef-building corals. And to make calcium carbonate, shell-building marine animals such as corals and oysters, they combine a calcium ion with carbonate from surrounding seawater, and they release carbon dioxide and water in the process. So in this sense, the building of skeletons in marine creatures, this is particularly sensitive to acidity. And like calcium ions, hydrogen ions tend to bond with carbonate, but unfortunately for those shell makers, they have a greater attraction to carbonate than calcium. And so when hydrogen bonds with carbonate, a bicarbonate ion is formed. Shell-building organisms can't extract carbonate ion that they need from bicarbonate, and this prevents them from using that carbonate to grow a new shell. In this way, the hydrogen essentially binds up the carbonate ions, and it makes it harder for shelled animals to build their homes. So even if animals are able to build skeletons in a more acidic water, let's say for example, they may have to spend even more energy doing this, and takes away from other activities like reproduction and just recreating themselves. If there are too many hydrogen ions around and not enough molecules for them to bond with, they can even begin breaking existing calcium carbonate molecules apart and dissolving shells that already exist. So when CO2 is sequestered, first, the pH of seawater gets lower as it becomes more acidic. Second, this process binds up carbonate ions and makes them less abundant in the ocean. These are ions that corals, oysters, mussels, and many other shelled organisms need to build shells and skeletons. So marine organisms possessing shells, all of those mollusks and crustaceans and corals, they need available carbonate ions to form the calcium carbonate that comprises their shells. So in essence, ocean acidification is robbing these organisms of their necessary building blocks. And we talked about sustainability being development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Well, the same can apply here to shells and organisms in the ocean. As the ocean acidifies, calcium carbonate molecules, the minerals that build the skeletons and shells of organisms like corals, oysters, sea urchins, and crabs, they dissolve more rapidly. So in simple terms, the ocean's uptake of carbon dioxide is causing an increased concentration of hydrogen ions. And this increase causes the seawater to become more acidic and causes carbonate ions to be relatively less abundant. When carbon dioxide is absorbed, chemical reactions occur, reducing that balance, the pH balance. That acidity reduces carbonate ion concentration, which is needed for shell building, and reduces saturation states for biologically important calcium carbonate minerals, making them more brittle, less durable. Hard corals are the reef-building corals, and their stone-like or hard structures, these are composed of calcium carbonate, the same substance that is found in shells of many of the marine organisms that you know about, including, like I said, oysters, clams, and snails, etc. So, ocean acidification is robbing corals and shell makers of their primary source of life, and maybe perhaps ours. So hopefully that helps break it down a little bit. I took a lot of this information from climateinterpreter.org, NOAA, NRDC, nature.com, and the Smithsonian Institute's ocean website. Have a look at any of those resources. I'll put all those down below. I tried to cram all those together to give you something that you could try to understand. It's a complicated topic, especially once we start diving into the chemistry, but how does this relate to you in the work that you're doing? Ultimately, if you want to protect the ocean, go back to reducing our emissions and cleaning up our supply chains, moving towards renewable energy and renewable inputs, and moving our economies towards a circular business model. that doesn't put as much greenhouse gas into the atmosphere, which will lighten the load or the burden that the ocean is carrying for us. All right, so that's how you can make a connection. I hope it helped. If you want to learn more things like this, or if you like this video, if you found it helpful, click the subscribe button down below. And if you want to learn more about sustainability, I've given you a link to a free download that we created. These are the 35 things that I think you need to know if you want to become or start making your way towards being an expert in sustainability, especially in the fashion industry or the apparel industry. I hope you'll take it, but hopefully you'll check back soon for more videos like this where I try to give advice and share everything that I've learned along the way. I want you to keep learning more about sustainability. So I'll see you next time. Thanks.